We're doing this manually now?
We're doing this manually.
Fantastic.
It adds an air of atmosphere, I think. When you've got to do something with a compass, I mean, it just makes it real science.
Get a picture of this.
So, that's north. Hang on.
How accurate is this exactly?
Well, the beam for this frequency is like half the sky.
So we'll be getting Betelgeuse,
Oh,
no
yes.
problem. Okay. All right, we are recording. Say hello, Emily.
Hello!
Right, fantastic. We are standing out here in the rain,
Live on scene.
live on scene. I can hear a very small voice in the background. What am I listening to, Emily?
You're listening to yourself, Chris.
Well, not just me. You too.
Not just me.
You too. Up there in the radio telescope dish, here at York University's Astro Campus, my phone is currently beaming episode 42 of the podcast out into the cosmos, which is awesome.
It's really cool.
Explain to me again how this works.
Right, okay.
This is totally legit, right? This is
Well,
really happening.
It is really happening. So normally what you can do is take a radio telescope and actually run it in reverse.
Yeah.
So instead of receiving signals from the universe, you can broadcast them to the universe.
Okay.
Now that takes some fancy electronics, which we don't currently have. So what we are doing instead is we are getting a phone to transmit microwaves. But that phone is stuck in the very, very center, the focal point of the dish, which means that signals are being beamed out by the dish into space.
So a couple of minutes ago when I phoned your office and a lovely colleague of yours answered the phone and then put the phone on the desk. Currently my phone is calling your office and playing the podcast to your office, which is weird enough as itself. But the reason we're doing that is because my phone actually has to be transmitting its microwave signal, which is what phones do, microwaves, out into, the atmosphere around us here on Earth. But because it's sitting in the focal point of a radio telescope dish, it's actually sending not the audio, but the microwaves, beaming that out into the universe. That's the idea.
That's the idea. And we're
Right.
pointing right in the direction of Betelgeuse.
Right. Now that's microwaves. Microwaves similar to radio waves?
Yeah, similar. They're just slightly shorter.
Right, but that'll totally legitimately work with this thing.
Oh, yeah, they're shorter than the mesh, which is on the dish, which is what all we need.
No problem. Okay, and so this radio dish, which is now a radio antenna, is pointed in the direction of the constellation of Orion.
That's right.
And we're doing that because this is episode 42, and as we have said before, episode 42 is important to us because Douglas Adams wrote a book quite some years ago now called The Hitchhiker's Guide to the Galaxy, in which the number 42 is very significant because... Why?
Because it is the ultimate answer.
Right, the answer to the ultimate question of life, the universe, and everything. Those of you who have read the book will know that the problem inherently in that is, what does the question even mean? But anyway, I won't give away that one entirely. Point is, we're doing this because in Orion there is a large red star called Betelgeuse. It's a red giant star.
It is a red giant.
And that is where two of the main characters in the book, Zaphod Beeblebrox and Ford Prefect, that's where they come from. They come from a small planet somewhere in the vicinity of Betelgeuse. And so we thought, to celebrate this, we would send something back to them as thanks for the bizarre story that is The Hitchhiker's Guide to the Galaxy. So for the next 40 minutes or so, episode 42 of Syzygy is beaming out across the cosmos to Betelgeuse. So how long is it going to take to get there?
So it's going to take something like 640 years.
640 years, because it's going at the speed of light, and Betelgeuse is approximately 640 light years away. So that's what that means.
Yeah.
640 light years means it's going to take 640 years for something moving at the speed of light to get there.
So the great thing is that by the time the podcast gets there,
Yep.
our whole perception of life, the universe, and everything could have completely changed.
That's right, actually. We might even know whether or not there's someone there to actually receive it on the other end. Okay, so that does lead me to my next question, Emily, the astronomer, which is, so how strong is this signal going to be by the time it gets there?
Well, unfortunately, not super strong. They're going to need some pretty good kit to pick it up.
Right, okay.
So this is something called the inverse square law for light.
Okay, take us through the inverse square law. This sounds like mathematics.
It is mathematics, but it's not too difficult to imagine. It basically means that for every meter that you go, you drop 1 over the distance squared in terms of signal.
So it's an inverse square, so that's a fairly strong drop-off. You can imagine it as, as the sphere is getting bigger, as this thing's being beamed out. If you imagine a balloon being blown up, for example, the size of that area of that balloon gets a lot bigger as the radius increases, right? Similarly with this signal, except that the signal's getting spread out over that spherical wavefront, over that increasing sized ball that we're sending out into the universe. And so that means it's getting weaker and weaker and weaker and weaker as 1 over the distance squared as we go out.
Yeah.
So
after 10
600
meters, then you're going to lose 100th.
Right.
You're going to be down to 100th of the signal.
Over 100 meters, you're down to 110. Okay, so 640 light years then?
It's going to be pretty weak.
Yeah, okay. But this is totally legit, right? This is completely
totally
going to work.
Yep.
Yep, okay. The other reason that we're doing this is to say a little bit of a thank you to everyone who has helped us to actually get this far. 42 episodes, that's more than just an experiment.
Yeah.
We've been doing this for more than a year now, up to episode 42, plus a few incidental ones along the way. And there are a few people who have helped us to do that. First of all, the University of York for actually allowing us to do this, on university property and in your working hours, which kind of works nicely. So thanks very much, University
With
of
our
York.
wonderful radio telescopes at Astro Campus.
Exactly. So huge thank you to the university and to Astro Campus. And one particular person here at Astro Campus who's been helping us out in the rain here this morning for a cup of tea as his reward. Who are we thanking?
Mark Lawson.
He's fabulous, the wonderful Mark.
He's our Astro Campus technician, so he knows supremely everything to do with our telescopes.
Right. And then there are our fabulous patreon.com patrons, the people who help to support the show financially and help us to keep the lights on. And so we have taken all of those people and we've added that to the end of the podcast. And so they are being beamed out as well across the cosmos in the vague general direction of Betelgeuse. And in 640 years' time, anyone receiving it at the other end will receive our thanks to them as well, which I think is kind of cool.
Yeah, and I think it's time to thank also all of our listeners, every single person who's turned on this podcast.
All of you guys as well. Yep. Thank you so much for listening. It's quite extraordinary.
It warms
frankly.
the heart to think that we're not just broadcasting to our mums and dads.
Exactly. I mean, we definitely are. There's no question. I don't know about your family, but my family definitely does listen in. But I have a feeling we have a few more people than that too. So thank you. Really, sincerely thank you. We didn't have time to really add everyone's name to the end, and we don't know who you are exactly anyway. But you can imagine your name added to the end of the podcast as one big thank you being sent off across the heavens. What else can we say?
No, it's raining. Let's go inside.
I think we probably should.